Hello everyone. So today we are going to look at this linear algebra question, which is to find the least square solution of the linear system 3x1 plus 5x2 equals 9, minus x1 plus 9x2 equals 20, and 4x1 plus 3x3 equals 8. Now, there is no exact solution to the system of equations. There's no x1 or x2 that will solve all three equations simultaneously at the same time. So we're looking for the quote-unquote best solution to the system, which is like sometimes it's like the closest solution to the subspace spanned by the column space of a system of equations. So I'm not really going to get into that theory so much, more like solving it. So let's go over. There's usually a couple ways of solving this. So we're going to establish a couple things. We're going to establish there's a matrix A that we're going to be working with, which is an n by n matrix, which is going to come from that system of equations. And B is an n by 1 matrix, or I'm sorry, m by 1. Sorry, let me make that a little clearer, m by 1. And yeah, so when you have an equation, ax equals b, there's always a least square solution. It's either going to be, if there's an exact solution to the system, then that's the solution. Not in this case, though, as I said. Or there's if it is not exact, it's the least square solution. So, two ways to solve for this system. Either you do number one, which is solving for x in the system ax equals atb, where a to the t, or maybe you want to look at it that way, is the transpose of the matrix A. Or number two, x equals ata inverse times atb. This works if A has a linearly independent column vectors. There's a theorem from linear algebra that says that if you have a matrix A that has linearly independent column vectors, then ATA inverse exists. Okay. Now, we are going to work on number one. Okay, number two, the issue with number two here with that method is not always will work out. Not only that, it's tedious to compute all that. So it's, in my opinion, it's best if you just work with one, So, you might say, great, you're talking about matrices, but where's my matrix? As I said, a matrix is going to come from our system of equations. So I'm just rewriting that system that you have as a product of two matrices equal to a third one. So in our case, this is the A that I'm speaking of. This is the B. And what you do is as follows. You're going to form ATAX and ATB. Sorry, just form ATA. So ATA, so matrix A was originally 3 by 2. So A transpose is going to be 2 by 3, because that's what a transpose does. It switches the number of columns and rows. And you multiply those matrices out, ATA, which gives you 26, 18, 18, 15. And then ATB now, you do that computation, you get 39 and 249. Okay. So then we're going to try to solve the system ATAX equals ATB. And basically you take the two results that you have and multiply them by a third vector, x1, x2, column vector. It's basically just the x1 and x2 that you're looking for as a solution. That's what x is. And equal to your ATB, so 39, 249, reading as a column. And then you try to solve. At this point, you can go and try any system that you have at your disposal. So if you want to use, inverse matrices, fine. If you want to use, or if you want to reduce this matrix, whatever, Cramer's rule, that's up to you. And then your answer will come out to be 3 over 2,666, and then your x2 value is 2,886 over 1,333. So those are your two values for x1, 3 over 2,666. For x2, 2,886 over 1,333. 333. So yeah, you'll get some nasty numbers from this really large fractions. That's very common. Okay, and that would be it. Now there are other ways to do this. You can go ahead and look at the projection formula that you have. Find the projection of a vector onto a subspace. That's also a possibility that you could have used here. So I'll just refer that. So again, projection of a vector onto a subspace, and then just so you just look that up. There's a little more to that, but I'll just give you those keywords for you to look at. But in my opinion, this is usually the like the safest, and if you mean easiest route to take, in my opinion. So yeah, I hope this helps. Thank you.